concept I want to introduce here, which is the shear center. Okay? So in this example, you have this two-cell cross-section. So you have this cell 1 here. We can say this is cell 1, this is cell number 2, for example. You have 4 booms. And you have a shear force, a transverse shear force of 100 kilonewtons, which is applied at the shear center of the cross-section. So basically the shear center is the location in the cross-section, where if you have the lift, for example, in a wing, applied at that point, at that shear center, it means the cross-section will not rotate, will not twist. Okay? It's a very important point because we don't want the airfoil or the wing to twist. Because if the wing twists, we lose the aerodynamic performance of the wing, right? We are changing the angle of attack, so we don't want that stuff to happen. So that's why when we design, for example, the wing box in a wing, one of the key things we need to bear in mind is the location of the shear center. Okay, make sure the lift is acting as close as possible to the shear center. Okay, so I'm going to show you in this example how, from this transverse shear flow analysis we have been doing, how we can quite easily, in fact, get the location of this shear center. That is one of the questions. The other question is, well, question A is quite easy. I'm asking you to calculate the second moment of area of this idealized multi-cell cross-section. Part B is what we did last week, determine the shear flow distribution. So comparing it last week, this example is different because we have 2 cells now. So last week we did only with 1 cell. And we also have this curved, this semicircle cell number 2, which is also something new. Okay? And then, yes, in part C of this question, I ask you to calculate the location of the shear center.
Could you repeat what's the shear center?
Yeah, shear center is, okay, you have the lift, right? On the wing, for example, right? You need to design your wing so that the lift, or the resultant of that lift, let's say, is located in the shear center. Why? Because, as I'm going to show you, if this force of 100 kilonewtons is located at the shear center, the cross-section will not rotate. The rotation or the twist angle is 0. Okay? So that's a very important point. Okay, so the first thing we need to do in this example is to, so let me scale this back. Okay, we need to define an initial orientation for our shear flows. So for example, let's say we define something like this. So this is my shear flow Q0, for example. Then it will cross boom 1. It will go this way. Let's call this shear flow Q1. Then it will cross boom number 2. And it will flow in this direction, Q2. It will cross boom number 3. Now, let's say Q3. Now, in boom number 4, part of the shear flow is going in this direction, Q0, which we have already there, right? And other part is going upwards here. And you can say this is my shear flow Q4, okay? So we have an initial orientation for all the shear flows in all the walls of our cross-section. And now what we need to do is we need to cross the booms, remember? Like we did last week, we need to be crossing all these booms. So in order to cross the booms, we need to have the second moment of area of cross section, right? So as you remember from last week, in idealized structures, I told you that the second moment of area about this x bar axis that we have here, okay, this x bar axis. For the second moment of area, we just account for the booms, right? Because in idealized structures, we are assuming the skins have zero thickness, right? Okay? So, these boom areas, they are given. So this boom number 1 and boom number 4, they have a boom area of 800 meters square. It's here, okay? And boom number 3 and boom number 2, they have a 600 square millimeters area. All right? So for the second moment of area, we will have, so if I look at these two, so I can draw the cross section here. So you have these two booms here with areas 800 square millimeters, right? I can put like this, and these other two booms here with areas equal to 600 square millimeters, right? Okay, this is the axis, neutral axis, our x bar axis. So we need to have, for the second moment of area, we need to have the distance of these booms to the neutral axis. That distance is quite easy, right? So from here to here, this is 150, right? This one from here to here is also 150. Okay? Same thing for the other two booms, boom 1 and boom 4. So now we can say, for example, if we look at these two booms here, this and this, contribution of these two booms for the second moment of area, the formula to get is the boom area times the square of the distance of the boom to the neutral axis. For each boom, we need to do this. The area of the boom times the square of the distance to neutral axis. So for these two booms, the area is 600 square millimeters. Right? The distance to the neutral axis is 150. I need to square the distance to the neutral axis. So because we have two booms in the same conditions, with the same area and the same distance to the neutral axis, I can just multiply this by 2 times. Yeah? Makes sense? But I still have two more booms with 800 square millimeters area. So I can say 800. The distance is also 150 square. Because they have two booms in these same conditions, I can also multiply by 2. So as you see, the calculation in idealized structures, the second moment of area is quite easy. Yeah? We just need to look at the booms, the contribution of the booms. Yes?
What are we going to test it on, the idealist structure, or are we tested on the more realistic?
In the exam?
Yeah.
Well, we did the more, what you call more realistic, I usually call the full effective or the original cross-section. We did some analysis, right? What I can ask you in the exam, for example, is I give you a simple, for example, say a rectangular hollow cross-section, okay? And I say, okay, build the idealizer. And then I ask you to calculate the transverse shear stresses on the realistic cross-section and on the idealized, and compare the two, for example. I can ask something like that. But of course, I need to give you not a very complex cross-section, right? Otherwise, you need 3 hours to do that, right? Yeah? That can be an option. Other option can be, I just give you, I idealize it like this, or I just give you a full effective cross-section. Ask you to get the shear flow distribution, for example. Yeah? Now that you talked in the exam, so my plan for the remaining weeks we have ahead, so today we are going to do these 2 examples in transverse shear flow, and then after this we are going to discuss the spar theory. Basically, you know, in a wing you have these big beams that we call spars, right? Running into the longitudinal direction. So we are going to derive a method to design that spars, because don't forget, we always try to design these components in aircraft to be as lightweight as possible, right? So what happens in these spars, they try to always design a spar with the thickness of the walls as thin as possible. Yeah? So what we are going to do, we are going to analyze the buckling of the spars next week. It's a very interesting topic. It's not difficult. I know that when you heard buckling, you buckle yourself, right? But yeah, don't panic. Don't panic, because you're going to see it's going to be a very interesting thing to see. Basically, what they do is we allow the spar to buckle, but it is a controlled buckling process. So we can reduce the weight as much as possible, okay? So that's the topic for next week. And then the other weeks we will do fatigue and fracture quite quickly, and air elasticity a little bit. And then we are done, okay? Yeah? So let's finalize these idealized structures, transverse shear flow. So we have the second moment of area. So can you please tell me how much is this result, please, for the second moment of area? Do you have any final result? (63 times 10 power 6 millimeters power 4, right? Yeah? It's easy to see the units. Look. Area, square millimeters, you are multiplying by square millimeters, right? So the end is millimeters power 4. Good. Now, we can start crossing the booms. So, you remember that equation for the transverse shear flow last week? This is a symmetric cross-section, right? So this x-bar axis is an axis of symmetry. So which means that the product of inertia is equal to 0. You also don't have any transverse shear force in the x direction. So this means that when you cross a boom, the shear flow after crossing the boom, let's say R plus 1, is going to be equal to the previous shear flow before crossing the boom minus the transverse shear force in the y direction over the second moment of area that we just calculated times the area of the boom that is being crossed times the distance of the boom to the neutral axis. Okay, so this equation comes after simplification of the general equation we derived last week by considering the symmetry of cross-section. And we have everything. So basically, if you send QR to the left-hand side, you can say the variation on the shear flow is going to be given by this equation, right? Yeah? Or the change on the shear flow when we cross the boom, this delta Q is going to be given by this equation. And we have everything. If you look carefully, look, we have, this is the transverse shear force, which is given, is this 100 kilonewton, right? This is the second moment of area we just calculated. This is the area of the boom. This is the distance to the neutral axis. So we have everything. We can start crossing the booms, right? Okay? So, for example, if we start crossing... Oh, there's one more thing. This is a two-cell cross-section, right? We have two cells here. So we need to... And this is a closed cross-section. So we have that problem with the initial shear flow, remember, from previous weeks? So we need to assign for each cell a shear flow that we are going to assume that we know already the value of that shear flow, or is given, okay? Yeah? So we need to do that for each cell. So let's say for cell number 1, I'm going to say, okay, Q1 is like the shear flow that is given. And for cell number 2 is going to be Q0, all right? So we have one shear flow per cell that we assume that we know already. Remember, this comes from that, remember when we did the open cross sections? We always started at the free edge, because before crossing a free edge, the shear flow is 0, right? We know it's 0. But in a closed cross section, we don't have free edges. And we need to have an initial shear flow to start our analysis. So that's why we need to assign for each cell an initial shear flow, like if we know how much that shear flow is, okay? All right, so now crossing, let's do this way, crossing boom number 2. If I cross boom number 2, what I will have is, if I look at this equation, is the shear flow after crossing boom number 2 is going to be the shear flow Q2. Needs to be equal to the shear flow before crossing the boom, which is Q1, minus transverse shear force, this one, minus 100 kilonewtons. 100, let's convert to newtons. Second moment of area is 63 times 10 power 6. Yeah. Area of the boom being crossed, we are crossing boom number 2, and the area of boom number 2 is 600. So times 600. Distance of boom number 2 to the neutral axis is 150, right? Yeah? So times 150. So we can say Q2 equal to Q1 plus, we will have 1 over 620, you agree? Times times 90,000, right? Yeah? Sorry? Is this correct or not? Someone said something. This one here? This one? So what I did was, so we have 10 power 5 in the numerator, right? 6. Huh? Oh, it's okay, sorry. I put 62 for some reason. Why? So this should be 63, not 62, right? So this will be 630. Yeah? Okay, yeah, you're right. Okay, so how much is this, please? So this will be, we can say Q2 is equal to Q1 plus, can you give me this? 142.8, yeah, it's fine. So we need to keep this result. Let's do like this. Okay. So I'm going to, I need space. I'm going to delete the second moment of area. Yeah. And I'm going to copy this result and save it here, okay? All right, so good. Now we need to continue crossing booms, so we can cross now boom number 3. In fact, from symmetry, we can say that the Q3 needs to be equal to Q1 from symmetry, but we can cross the boom 3 and we can see if that is the case, okay? So let's crossing boom 3. If you do that, you get what? Shear flow after crossing the boom is Q3. Shear flow before crossing the boom is Q2. Now this I can write like this because the transverse shear force is the same, 100 kilonewtons. Second moment of area of the cross section is the same. So we get this. The area of boom number 3 is 600. The distance to the neutral axis, this is important now. We need the distance, not the square of the distance, right? So boom number 3 is below the neutral axis, so the distance should be minus 150. Okay? Yeah? This is an important point. So if I replace now Q2 in this equation with Q1 plus 142.8 we obtained before, I get Q3 is going to be equal to Q1 plus 142.8. And this term here is minus 142.8. So it means Q3 is going to be equal to Q1, as expected from symmetry, right? Yeah? Make sense?
Is that 150 supposed to be square?
No.
It's not, right?
Square is only in the second moment of area. Yeah? In this equation, look, in this equation for the shear flow is only the distance, and you need to be careful with the signal. Yeah? If it is below the neutral axis, it should be negative. Okay, so we can also say that Q3 is going to be equal to Q1. We can also save this result. Now, we need to continue crossing booms. So let's move now to boom number 4. Let's cross boom number 4. So crossing boom 4. What do we have in boom number 4? So boom number 4 is sharing 3 walls, right? So we need to say on the left hand side, look, on the left hand side of this equation for the shear flows, we have the shear flows leaving the boom. On the right hand side, we have the shear flows getting into the boom, getting in the boom, right? Arriving at the boom, okay? Now if you do that for this boom number 4, we have shear flows leaving the boom is Q4 and Q0, yeah? You see? So I'm putting all of these shear flows leaving boom number 4 on the left hand side. On the right hand side, I have the shear flow arriving at the boom, which is shear flow Q3, which we know is equal to Q1. Yeah? I can do like this, right? And now I just need to include this term here because I'm crossing boom number 4, right? Yeah? So this term is going to be plus 1 over 630 again. So this is same shear force, same second moment of area. But now the area of boom number 4 is 800. It's not 600, it's 800. And the distance of this boom to neutral axis is minus 150. Yeah? Okay? Make sense? Yeah. So we have, what I can do in this equation is I can leave on the left-hand side Q4. That's what we are looking for. I can send to the right-hand side Q0. Don't forget Q0 is one of our unknowns. Is the initial shear flow for cell number 2. So we will have Q1 minus Q0 minus 800 times 150 over 630. Yeah? So it means Q4 is going to be equal to Q1 minus Q0 minus, can you please tell me how much is this? 800 times 150 over 630? Sorry? 190.5, right? Yeah? You all agree with this or not? So we can also save this result because we are going to need this. Copy. Let's say, maybe I can delete these guys now. Okay, so look at these three equations we have here. So basically we have on the left-hand side of these equations, we have shear flows Q2, Q3, Q4. And on the right-hand side, we have the initial shear flows Q0 and Q1, which we assumed at the beginning that they were given to us, right? So I need now to find a way to calculate this Q0 and Q1. And if I do that, I unlock all the other shear flows, right? Yeah? Make sense? And there's where now comes this shear center thing. And also, there's when we are going to need to use the equation for the gradient of the twist angle. We remember we derived this when we discussed the torsion. Yes?
Sorry. Why would you assume that Q3 is equal to Q1?
From symmetry. Yeah, from symmetry. But we also derive. I deleted now, but you will have in the movie. I also, when I was crossing boom number 3, remember? Yeah. You arrive at the the conclusion that Q3 equal to Q1. After crossing boom number 3, okay? That is in the video. You can review it on, okay? But from symmetry, you can say that. All right. So, yeah, this gradient of twist, we derived this when we discussed the torsion, remember? And I told you the equation is 1 over 2 times the area of the cell times the model of rigidity, okay? And then this we'll need to do this contour integral. I'm quite sure you remember this, of Q, which is the shear flow over the thickness, and this needs to be integrated along the walls or the contour, right? You remember we did use this equation in torsion. That's why we did torsion before we do this, because you need this equation now to solve this example. Why? Because the transverse shear force is applied at the shear center, and I told you that when that is the case, this twist angle is 0. Yeah? The cross section does not rotate. So what we are going to say is that this twist angle for cell 1 and cell 2 needs to be equal to 0. This is only true because the transverse shear force is applied at the shear center. Okay? And we are going to say something like this. The gradient of twist for cell number 1 needs to be equal to 0. One equation. The gradient of twist for cell number 2 needs to be equal to 0. Second equation. Why do we need two equations? Well, because we have two unknowns, which are Q1 and Q0. Yeah? At the end, we will have two equations for these two unknowns, and then we solve the problem. For part B, we still don't know where is the location of the shear center, right? But it doesn't matter for this now, because the only thing which is important is transverse shear force is located at the shear center, so it means the cells will not rotate. The twist is 0. So we just need to write this. So let's start with this first cell. So for the first cell, so we are going to assume, so maybe I can use the green color. We are going to assume at the beginning the rotation for this twist angle is going to be anti-clockwise. Let's assume positive rotation anti-clockwise. So in fact, there is this 1 over 2 Ag that you have in this equation. Because, look, because you are going to have this times the contour integral, which we are going to do here. We are going to do here the contour integral, okay? This is going to be equal to 0, right? So in fact, because this is going to be equal to 0, I can just ignore this guy, isn't it? Yeah? Because if I send this guy to the left, the right-hand side, it's going to be multiplied by 0. Well, I can only do this because this model of rigidity is the same for this cell number 1, for these 4 walls in cell number 1. This model of rigidity is the same. And also because the area of the cell, of course, is the same for that cell. That is quite obvious, right? But for example, if I imagine, for example, you are doing a wing with, let's say, for example, this wall here is made of titanium, for example, while these 3 other walls are made of composite materials. So in that case, you cannot say this is going to be, yeah, because the model, this G model of rigidity will be different for the different walls. So you cannot cancel, right? Yeah. So careful with that. But for this example, no problem. These guys go away. So the only thing we need to do basically is to do this contour integral. And this contour integral is quite easy. Look at this. Let's start with this vertical wall. Let's start with this horizontal wall, Q1, this wall here. So I have, what is the shear flow in that wall is Q1. Yeah? What is the length of that wall? So I need to have multiply by the length. That's why I have this ds here. What is the length of this wall? It is 400 millimeters. Yeah? I need to multiply this by 400. And I need to divide now by the thickness. Yeah, it is. But yeah, because this is the idealization here, we assume is 0. Yes. So that we can use only the booms, for example, for the second moment of area. But for the torsion, I understand your question completely. For the torsion, we need to go back to the original cross-section because that affects the twist angle, okay? So we need to go back to the original cross-section. That must be said here somewhere. Yeah. The walls have all the same uniform constant thickness of 2 millimeters, which is even easier in this example. So what I can do is, so all of these walls will have the same 2 millimeters thickness. So basically this will, what I can do is, I can say then, I can put all the 2 millimeters, right, outside here because it's going to be common for the 4 different walls. And then at the end here, I will only have this, for this wall number 1. Now for next wall, this wall, where we have Q2, right? So we can replace Q2 by this equation we have here for shear flows. So we will have plus Q1 plus 142.8 times the length of that wall, which is 300 millimeters. Now, this wall here in the bottom, where we have Q3, so I'm going to continue here. Q3 is equal to Q1, so I can put Q1 times the length of that wall, which is 400 millimeters, yeah? And last wall we have is this one, this vertical wall, where we have Q4, but Q4 is equal to Q1 minus Q0 minus 190.5, and the length of that wall is 300. This should be equal to 0. Yeah? That is the contour interval. Quite easy, isn't it?
Sir,
Yeah.
why did you take out the teeth divided by C?
Sorry?
You didn't include the teeth thickness.
Thickness is here. Because the thickness of these four walls is the same, all walls have the same thickness. Yeah? So I could have divided everything by 2, right? Yeah, I could have done this. But because then I can just send these two to the outside, right? And then that's why I have these two over here, right? Yeah? This is the thickness, yeah? In this case, all walls have 2 millimeters thickness. So I can do this. Okay, so we will have this. So why did I do this? Because now I can get rid of this 1/2, right? Make our life a little bit more easier. So this equation, we need to keep this equation because let's make it as small as this. Yeah? I can do even better. Okay? So this equation here, we are going to need it. And the second equation is now obtained for the second cell. So we need to do the same analysis for second cell. So we are going also to assume an anti-clockwise rotation for the angle, for the twist angle on this second cell. So we will have what? So the contour integral. We have two walls here. This one where we have Q0, starting with this one. So we will have, I can do this way for this one, Q0 times the length of this wall. So how much is the length of this wall? What do you think? Times pi, times what? 150, which is the radius, isn't it? Yeah? Oops. Yeah. Yeah, because my drawing capabilities are a bit limited. But this is a Smith circle, okay? Yeah. So times 150, which is the radius, over the thickness. Now I can put the thickness here inside, it's fine. And now the other wall is this one. Okay? Now, this shear flow Q4 is going to be opposite with the anti-clockwise rotation of the cell. You agree with me? So we need to use a negative, this minus now, okay? Yeah? You understand? So we are assuming for the cell that anti-clockwise rotations are going to be positive. This shear flow Q4 for cell number 2, yeah, is going to rotate cell will tend to rotate cell number 2 in a clockwise direction, which is opposite to our anti-clockwise. That's why you have the minus there, okay? Yeah, and now we have Q4, which is Q1 minus Q0 minus 190.5 times the length, which is 300, over the thickness, which is 2. And that's all we have in cell number 2. This needs to be equal to 0. Okay? To 0 because our transverse shear force is located at shear center, and cell number 2 will not rotate in that case. Yeah? Are you guys following this or not? Yeah, and now basically you just need to solve this. You have here a system of equations, 2 equations for 2 unknowns, Q0, Q1. You just need to solve this, but I can save us some time because the results I have here for Q0 is minus 76.45 Newton per millimeter. And for Q1, the result I have is minus 6.1 Newton per millimeter. Don't forget, shear flow is a force per unit length. Okay? So these are the results if you want to do at home to check. These are the results I have. So now if you replace Q0 and Q1, you can calculate Q2 in this equation here at the top, right? Yeah? So if you do that, you get Q2 equal to 136.7 Newton per millimeter. Q3 is equal to Q1, so we can say Q1 equal to Q3 equal to minus 6.1 Newton per meter. And Q4 is going to be equal to minus 120 Newton per millimeter. Okay? Yeah? So what you can do is, if you want, you can now... So Q0 minus 76.45. So you need to revert the direction of Q0, and you put here 76.45 Newton per millimeter, okay? Q1, also negative, minus 6.1, so 6.1. Q3 equal to Q1, so also equal to minus 6.1. So Q3 is also going to be in this direction, 6.1. Q2, 136.7 positive, so Q2 is going to be in this direction, 136.7. And Q4, negative and minus 120. So initially we have put Q4 upwards because we got a negative, we put downwards and 120. Yeah, makes sense? Remember, initially we assumed Q4 going upwards. Because we obtained the negative Q4, it means we need to reverse the orientation of Q4 and going downwards, all right? Yeah? So, yeah.
It's just the first case, it doesn't do like the circle. You know, it doesn't go circle around the rectangular box. It's like...
For the first cell.
Yeah. Because back in the time, usually we just went around the rectangle and not just...
Yeah.
I know you don't want to.
Yeah. But don't forget also there is a contribution of the 76.44 that is also propagated to cell 1. So it's difficult to see that way. Yeah? Yeah, but at the end, if you calculate again the gradient of twist with this result, you need to get the 0 twist for both cells, right? because we obtained Q0 and Q1 from that condition, right? Yeah. Good? Now, part C, location of the shear center. So, let's think a bit about it. What we are looking now is basically what is this EX that you have there. That will give you the location of the shear center, that point. So don't forget EX is starting on this vertical wall 2, 3, right? So vertical wall 2, 3 is equivalent to having EX equal to 0, right? Okay? So, you have any idea of how we can get the location of the shear center now for part C? What do you think we can do? Yes?
Take the moments.
Take the moments. Yes, very good. Take the moments. Right? So we are going to take the moments, and basically from the equilibrium of the moments, we should be able to get EX. And that EX is going to be the location of the shear center. Yeah, you might be thinking, okay, the equilibrium of the moments will always give me the location of the shear center. So careful here, because what really is giving us the location of the shear center is these two conditions that we imposed on the twist angle, right? Equal to 0 for the two cells. These two conditions that we imposed here in part B led us to this system of equations, which led us to obtain Q0 and Q1 such that twist angle is going to be 0 for two cells, right? Now, in top of that, everything needs to be in equilibrium, yeah? Always. So the location of the shear center will come from the moment equation, yeah, right? But you will get the right location essentially because of these two conditions, right? That you applied before, okay? So, maybe I can delete, I need some space now to delete this. So, we are going to use this equation, which is summation of moments produced by the shear flows needs to be equal to the summation of moments produced by the external transverse shear force. Okay? And we need to decide which point we are going to use to calculate these moments. I think point 3 or point 2 is good point. Okay? So for example, about point 3, summation of moments produced by the shear force about point 3 equal to the summation of moments produced by the external shear force. Don't forget this. The contribution for the moments from the internal shear flows we obtain from this expression. 2 times the area times the shear flow. Okay? Remember this? We did this last week, yeah? So let's start with... So before we start, this shear flow and this shear flow, they are passing on boom number 3, point number 3, so they don't produce moment about point number 3, right? That is the first thing. Now, what is the moment produced by this shear flow on this top wall 2-1, about boom number 3? We need to define, so we always need to use boom number 3, and we need to use the booms sharing the shear flow, this shear flow, right? Which are boom number 2 and boom number 1. We need to use these 3 booms, so we connect these 3 booms. And the area that we need to use in that moment equation is the area of this triangle. Remember, we did this last week as well. Yeah? So keep this triangle in mind. So we need to get this area. And the moment is going to be clockwise, you agree? Clockwise, so minus 2 times the area of that triangle, which is 300 times 400 over 2. Yeah? Times the shear flow in that wall, which is 6.1. That's it. This is the moment calculated by this 6.1 Newton per millimeter shear flow. Now, the next one we can do is this 120 in this wall 1/4. Also clockwise moment, so minus 2 times the area. Which area do we need now? Again, boom number 3, always. We are evaluating the moment about boom number 3. And we need to use boom number 1 and boom number 4, which are the 2 booms sharing the wall where you have 120 shear flow acting there. So the area that we need to use is the area of this triangle. Yeah? Okay? So which is, again, 300 times 400 over 2, and the shear flow in that wall is 120. Quite easy, isn't it? And the last one for the shear flows, last one I need to do is this, the moment produced by the 76.45 shear flow, about 0.3. This can be a bit tricky. So which booms do I need, which area do I need to use to calculate the moment? Well, I need to use boom number 3, and this shear flow is being shared by boom number 1 and boom number 4. So the area that I need to consider is this one. This triangle plus this, the area of this semicircle. Yeah? You see? So this area, yeah, makes sense or not? So shear flow is going to be clockwise as well. 2 times the area, first area of the triangle is, so we might need to open a bracket here, 300 times 400 over 2, plus the area of this semicircle, which is, so the area of a circle is P times the radius square. Radius is 150, right? So this is the area of a circle. Semicircle is half of this, right? Yeah? This is the area. What is the shear flow acting there is 76.45. Okay? Not difficult, isn't it? And shear flows, that's it. That's all we have for the shear flows. Now, the right-hand side of this moment equation is the moment produced by the external forces about same point, 0.3. And that is a quite easy moment to do, right? The external force is this 100 kilonewton. The moment is, how much is it? Clockwise as well, right? So minus, what is the distance? Ex times the force, which is 100 kilonewtons, right? Yeah? And this is the, if you look carefully, the only unknown that you have in this equation is the location of the shear center. Okay, after this, you can get a job in Airbus. Yeah? If you're going to work on structures, that's what they are looking for mostly. Well, they are looking at air elasticity as well. We are going to discuss that. But this is a very important thing, shear center, okay? and this is how you get it. Yeah? So you can imagine when they come up with a new design of a wing and wing box, they need to do a lot of iterations, right, in the actual wing. So they want to do very quick calculations, right? That's why structural idealization is important, because these are simple things you can put in MATLAB or in Excel, right? And get these shear flows and location of shear centers. Location of shear center is not good, so then you can do another iteration, go Excel to do automatically these calculations for you. This kind of stuff they do there, okay? Once you are confident of everything, then you can go to a FEA package like Abacus. They use Abacus a lot. Airbus is the software they use for structures. They can go to Abacus and do a full model, right, using shell elements, doing the very refined meshes, because they are very confident of the final geometry of the wing, right? So they can do a very accurate, detailed model in Abacus to get final validation. And on top of that, they go and do experimental tests as well. They have to, right? Yeah.
You know, when you pick point number 3,
Point number 3, yeah.
and then you use the upper triangle first.
Yes.
How do you know which one to use?
Yeah, you need. Yeah, the rule is. So maybe I can delete. Okay, I can delete this stuff here, right? The rule is. For example, we had here this shear flow 6.1 in this wall, right? You want to calculate the moment produced by this shear flow. So the rule is, you need to select 3 booms to define that area. The first boom is always the boom where you are evaluating the moments, in this case boom number 3. The other 2 booms, so look, this wall here, where you have this 6.1 Newton per millimeter, in these walls you have boom number 2 and boom number 1. These are the other 2 booms you need to always have. Okay? And then you just connect these 3 booms, and then the area is the area that you get after connecting these 3 booms. Yeah? For that curved one, for this shear flow you had here, which I think it was 74 something, right? 76.45. Is the same thing. If you look carefully, is boom number 3, because you are calculating the moment about boom number 3. And this wall here, the booms that you have sharing this wall is boom number 1 and boom number 4. So you connect these 3 booms, but here you need to be careful, because the wall, what have I done? Yeah. For the area, you need to use this wall, and the wall where you have the shear flow is this, is not this, right? Yeah? And this other wall. So that's why you need this total area here, right? Okay? You need, sometimes you have this, you can have this error. So you have these 3 booms, boom number 3, number 1, and number 4. You tend to use this area only. But that is not correct. Why? Because this area is for the shear flow in this wall, which was 120. And you are not calculating the moment produced by this 120. You are calculating the moment produced by this 76.45. So the area you need to use is this total area, because this is the wall. This is the wall where you have this 76.45 shear flow, right? Yeah? Okay? I have a problem here now, which is we have 30 minutes, basically. That is not enough for the other example, which is even more complicated than this. So what we can do is, we don't do a break today. I just introduce the other example, give you some steps, critical steps you need to follow to solve it. Yeah? You try to solve at home, and next week we can start from there. Okay? Yeah. So we don't do a break today. We can leave a bit earlier. This week was a bit atypical because of that talk at the beginning.